Introduction to semiconductors. Since the 1960s, when the transistor became common in consumer devices, semiconductors have acquired a dominating role in electronics. The term semiconductor arises from the ability of certain materials to conduct some of the time, but not all of the time. We can control the conductivity to obtain amplification, rectification, oscillation, signal mixing, switching, and other effects. The semiconductor revolution. Decades ago, vacuum tubes, also known as electron tubes, were the only amplifying devices available for use in electronic systems. A typical tube, called a valve in England, ranged from the size of your thumb to the size of your fist. You'll still find tubes in some power amplifiers, microwave oscillators, and video display units. Tubes generally required high voltage in order to operate efficiently. Even in modest radio receivers, it took at least 50 volts DC and more than 100 volts DC or more to get a tube to work. Such voltages mandated bulky, massive power supplies and created an electrical shock hazard. Nowadays, a transistor of microscopic dimensions can perform the functions of a tube in most low-power electronic circuits. The power supply can comprise a couple of AA flashlight cells or a 9-volt transistor battery. Even in the high-power applications, transistors have smaller dimensions and weigh less than tubes having similar signal output specifications. Figure 19.1. A power amplifier transistor at left has a much smaller volume and mass than a vacuum tube of comparable signal output capacity. Top of page 336. Integrated circuits, ICs, hardly larger than individual transistors, can do the work of hundreds, thousands, or millions of vacuum tubes. You can find an excellent example of IC technology in personal computers and in the peripheral devices you will use with them, such as displays, external disk drives, printers, and modems. Vacuum tubes enjoy some advantages over semiconductors even today. We can momentarily exceed the voltage, current, or power rating of a vacuum tube, and the device will usually forgive us, while a semiconductor device in a similar application might die immediately. A few audio enthusiasts, especially in popular music bands, insist that amplifiers made with vacuum tubes produce better quality sound than similar amplifiers made with semiconductor devices. Semiconductor materials. Various elements, compounds, and mixtures can function as semiconductors. Two common semiconductor materials are silicon and a compound of gallium and arsenic known as gallium arsenide, abbreviated GaAs. In the early years of semiconductor technology, germanium formed the basis for many semiconductors, but today we rarely see it. Other substances that work as semiconductors include selenium, cadmium compounds, indium compounds, and other oxide of certain metals. Silicon is an element with an atomic number 14 and atomic weight 28. In its pure state, silicon appears as a lightweight metal similar to aluminum. Pure silicon conducts electric current better than dielectric material does, but not as well as most metallic conductors, such as silver, copper, or aluminum. The Earth's crust contains silicon in great abundance, and we can mine it from some crustal rocks and sand. In its natural state, silicon almost always exists tied up as compounds with other elements. Industrial vendors extract the pure element. Electronic component manufacturers mix other substances known as impurities with silicon to give the semiconductor material specific properties. The resulting solids are cut into thin slices known as chips or wafers. Gallium arsenide. Another common semiconductor is the compound gallium arsenide. Engineers and technicians write its acronym like the chemical symbol GaAs and pronounce it aloud as gas. If you hear about gas FETs or gas ICs, you're hearing about gallium arsenide technology. Gas devices perform better at higher frequencies than silicon-based devices do, because electric current can travel faster through gas than silicon compounds. Gas devices are relatively immune to the direct effects of ionizing radiation, such as X-rays and gamma rays. Selenium. Selenium is a chemical element whose electrical conductivity varies depending on the intensity of visible ultraviolet, UV, or infrared radiation that strikes it. All semiconductor materials have this property known as photoconductivity to some degree, but in selenium the effect is pronounced. For this reason, selenium constitutes an excellent choice for the manufacture of photocells. Selenium can also work well in certain types of rectifiers that convert AC to DC. Selenium has exceptional electrical ruggedness, meaning that it can withstand short-lived electrical overloads, such as too much current or voltage. Selenium-based components can survive brief transients or spikes of abnormally high voltage better than components made with most other semiconductor materials. Germanium. Pure elemental germanium constitutes a poor electrical conductor. It becomes a semiconductor only when we add impurities. In the early years of semiconductor technology, engineers used germanium-based components far more often than they do now. In fact, we'll rarely encounter a germanium device in any electronic system today. High temperatures, such as soldering tools generate, can destroy a germanium-based diode or transistor. Metal oxides. Certain metal oxides have properties that make them useful in the manufacture of semiconductor devices. When you hear about MOS, pronounced MOS, or CMOS, pronounced CMOS, technology, you're hearing about metal oxide semiconductor and complementary metal oxide semiconductor devices, respectively. Certain types of transistors and many kinds of ICs make use of MOS technology. In integrated circuits, MOS and CMOS construction allows for a large number of discrete components such as resistors, inductors, diodes, and transistors on a single chip. Engineers say that CMOS has high component density. Metal oxide components need almost no current in order to function. When we use a battery to power a small MOS-based device, the battery will last almost as long as it would if we let it sit on the shelf and didn't use it for anything. Most MOS-based devices can work at extreme speeds, allowing for operation at high frequencies in radio frequency RF equipment and facilitating the rapid switching that's important in today's computers. All MOS and CMOS components suffer from one outstanding limitation. A discharge of static electricity can destroy one of them in an instant. We must use care when handling components of this type. Any technician working with MOS and CMOS components must wear a metal wrist strap that connects one wrist to a good earth ground, so static electric buildup cannot occur. Doping and charge carriers. Impurities give a semiconductor material the properties that it needs to function as an electronic component. The impurities cause the material to conduct current in certain ways. When manufacturers add an impurity to a semiconductor element, they call the process doping. The impurity material itself is called a dopant. Donor impurities. When a dopant contains an inherent excess of electrons, we call it a donor impurity. Adding such a substance causes conduction mainly by means of electron flow, as in an ordinary metal such as copper. The excess electrons move from atom to atom when a potential difference exists between two different points in the material. Elements that serve as donor impurities include antimony, arsenic, bismuth, and phosphorus. A material with a donor impurity is called an N-type semiconductor because an electron carries a unit negative electric charge. Acceptor impurities. If an impurity has an inherent deficiency of electrons, we call it an acceptor impurity. When we add an element such as aluminum, boron, gallium, or indium to a semiconductor element, the resulting material conducts mainly by means of hole flow. A hole comprises an assigned spot in an atom, where an electron would exist under normal conditions, but in fact doesn't show up there. A semiconductor with an acceptor impurity is called a p-type semiconductor because a hole has in effect a unit positive electric charge. Majority and minority carriers. Charge carriers in semiconductor materials always constitute either electrons or holes. We never see oddball charge carriers, such as protons or helium nuclei in electronic devices, although we do encounter them in high energy physics. In any semiconductor substance, some of the current takes the form of electrons passed from atom to atom in negative to positive direction, and some of the current occurs as holes that move from the atom to atom in a positive to negative direction. Sometimes electrons account for most of the current in a semiconductor. This situation exists if the material has donor impurities, that is, if it's of the N type. In other cases, holes account for most of the current. This phenomenon occurs when the material has acceptor impurities, making it a p-type. We call the more abundant or dominating charge carriers either electrons or holes, the majority carriers. We call the less abundant ones the minority carriers. The ratio of majority to minority carriers can vary depending on the exact chemical composition of the semiconductor material. Figure 19.2 shows a simplified illustration of electron flow versus hole flow in a sample of N-type semiconductor material, where the majority carriers constitute electrons and the minority carriers constitute holes. Each point location in the grid represents an atom. The solid black dots represent electrons. Imagine them moving from right to left as they jump from atom to atom. Small open circles represent holes. Imagine them moving from left to right as they jump from atom to atom. In the example, the positive battery or power supply terminal, the source of holes, would lie somewhere out of the picture toward the left, and the negative battery or power supply terminal, the source of electrons, would lie out of the picture toward the right. The p-n junction. Connecting a piece of semiconducting material, either P or N-type, to a source of current can provide us with phenomena for scientific observations and experiments. But when the two types of material come into direct contact, the boundary between the p-type sample and the n-type sample, called the p-n junction, behaves in ways that make semiconductor materials truly useful. The semiconductor diode. Figure 19.3 shows the schematic symbol for a semiconductor diode, formed by joining a piece of p-type material to a piece of n-type material. The n-type semiconductor is represented by the short straight line in the symbol. We call it the cathode. The p-type semiconductor is represented by the arrow. We call it the anode. Electrons can move easily in the direction opposite the arrows, and holes can move easily in the direction toward which the arrow points. Electrons normally do not move with the arrow, and the holes normally do not move against the arrow. If you connect a battery and a resistor in series with the diode, you'll get a current to flow if you connect the negative battery terminal to the diode cathode and the positive terminal to the anode, as shown in figure 19.4a. A series-connected resistor eliminates the risk of diode destruction by excessive current. No current will flow if you reverse the battery polarity, as shown in 19.4b. It takes a specific well-defined minimum applied voltage for conduction to occur through a semiconductor diode, in the situation shown by figure 19.4a. We call this threshold potential difference the forward breakover voltage. Depending on the type of semiconductor material, the forward breakover voltage for a particular diode can vary from about 0.3 volts to 1 volt. If the volt across the p-n junction falls short of the forward breaker voltage, the diode will fail to conduct current even when we connect it, as shown in figure 19.4a. This effect, known as the forward breakover effect or the p-n junction threshold effect, allows us to build circuits to limit the maximum positive or negative peak voltages that signals can attain. We can also take advantage of this effect to construct a device called a threshold detector, in which a signal's positive or negative peak amplitude must equal or exceed a certain minimum in order to pass through. How the junction works. When the N-type material has a negative voltage with respect to the P-type, as in figure 19.4a, that exceeds the forward breakover voltage, electrons flow easily from N to P. The N-type semiconductor, which already has an excess of electrons, receives more. The P-type semiconductor, already suffering from a shortage of electrons, gets deprived of still more. The N-type material constantly feeds the electrons to the P-type in an attempt to create an electron balance, and the battery or power supply keeps robbing electrons from the P-type material in order to sustain the electron imbalance. Figure 19.5a illustrates this condition known as forward bias. Current can flow through a forward biased diode easily under these circumstances. When we reverse the battery or DC power supply polarity, so the N-type material acquires a positive voltage with respect to the P-type material, we have a condition called reverse bias. Electrons in the N-type material migrate toward the positive charge pole, away from the p-n junction. In the P-type material, holes drift toward the negative charge pole, also away from the p-n junction. The electrons constitute the majority carriers in the N-type material, and the holes are the majority carriers in the P-type material. The charge therefore disappears in the vicinity of the p-n junction, as shown in figure 19.5b. This charge-free zone, where majority carriers are deficient, is called the depletion region. A shortage of majority carriers in the semiconductor substance means that the substance cannot conduct well, so a depletion region acts like an electrical insulator. The phenomenon reveals the reason why a semiconductor diode will not normally conduct when reversed biased. A diode from a one-way current gate usually. When the cathode and anode of a p-n junction have the same electrical potential as applied from an external source, we call the condition zero bias. Junction capacitance. Some p-n junctions can alternate between conduction in forward bias and non-conduction in reverse bias, millions or billions of times per second. Other p-n junctions can't work so fast. The maximum switching speed depends on the capacitance at the p-n junction during conditions of reverse bias. As the junction capacitance of a diode increases, the highest frequency at which it can alternate between the conducting state and the non-conducting state decreases. The junction capacitance of a diode depends on several factors, including the operating voltage, the type of semiconductor material, and the cross-sectional area of the p-n junction. If you examine figure 19.5b, you might get the idea that the depletion region sandwiched between two semiconducting sections can play a role similar to that of the dielectric in a capacitor. If so, you're right. A reverse-biased p-n junction forms a capacitor. Some semiconductor components, called a varacitor diodes, are manufactured with this property in mind. We can vary the junction capacitance of a diode by changing the reverse bias voltage, because this voltage affects the width of the depletion region. As we increase the reverse voltage, the depletion region gets wider and the capacitance goes down. Avalanche effect. Sometimes a diode conducts even when reverse biased. The greater the reverse bias voltage, the more like an electrical insulator a p-n junction gets, up to a point. But if the reverse bias reaches or exceeds a specific critical value, the voltage overcomes the ability of the junction to prevent the flow of current, and the junction conducts as if forward biased. Engineers call this phenomenon the avalanche effect, because the conduction occurs in a sudden and massive way, something like an avalanche on a snowy mountain. Avalanche effect does not damage a p-n junction unless the applied reverse voltage is extreme. It's a temporary thing. The depletion region appears while avalanche breakdown occurs, but when the voltage drops back below the critical value, the junction behaves normally again. If the bias remains reversed after the avalanche breakdown condition ends, the depletion region returns. Some diodes are designed to take advantage of the avalanche effect. In other cases, avalanche effects limits the performance of a circuit. In a device called a Zener diode designed specifically to regulate DC voltages. You'll hear or read about the Zener voltage specification. The value can range from a couple of volts to well over 100 volts. Zener voltage is theoretically equivalent to avalanche voltage, but in the case of a Zener diode, the manufacturer tailors the semiconductor material so as to produce an exact, predictable avalanche voltage. For rectifier diodes in power supplies, you'll hear or read about the peak inverse voltage, PIV, or peak inverse voltage, PRV specification. That's the highest instantaneous reverse bias voltage that we can expect the device to withstand without risking avalanche breakdown. In practical applications, rectifier diodes must have PIV ratings great enough so that avalanche effect will never occur, or even come close to happening during any part of the AC cycle. Okay, now I'm just reading right into Chapter 20, which is diode applications. In the early years of electronics, most diodes comprised vacuum tubes. Today, most diodes are made from semiconductor materials. Contemporary diodes can do almost everything that old vacuum tubes once could, and a few things that people in the tube era never imagined. Rectification. A rectifier diode passes current in only one direction, as long as we don't exceed its specifications. This property makes the device useful for changing AC to DC. Generally speaking, when the cathode has more negative charge than the anode, current flows. When the cathode has a more positive charge than the anode, current does not flow. The constraints of this behavior are, as we've learned, the forward, breakover, and avalanche voltages. Examine the circuits shown in Figure 10, 1a. Suppose that we apply 60 Hz AC sine wave to the input terminals. During half of the cycle the diode conducts, and during the other half it doesn't. This behavior cuts off every cycle. Depending on which way we connect the diode, we can make it cut off during either the positive half of the AC cycle or the negative half. Figure 21b is a graph of the output of the circuit shown at A. The circuit and wave diagrams of Figure 21 involve a half-wave rectifier circuit, which is the simplest possible rectifier. Simplicity constitutes the chief advantage of the half-wave rectifier over other rectifier circuits. You'll learn about various types of rectifier diodes and circuits in the next chapter. Detection. One of the earliest diodes existing, even before vacuum tubes, was made partly with semiconductor material, known as cat's whiskers. The device comprised a fine piece of wire in contact with a small fragment of the mineral galena. This contraption had the ability to act as a rectifier for extremely weak RF currents. When experiments connected the cat's whiskers in a configuration such as the circuit of Figure 20-2, the resulting device could receive amplitude-modulated radio signals and produce audible output in the headset. The galena fragment, sometimes called a crystal, gave rise to the nickname crystal set for this primitive radio receiver. You can build a crystal set today using an RF diode, a coil, a tuning capacitor, a headset, and a long wire antenna. The circuit needs no battery or other source of electrical power. If a broadcast station with a reasonable power transmitter is located within a few miles of the antenna, the received signal alone produces enough audio to drive the headset. For ideal performance, the headset should be shunted with a capacitor whose value is large enough to short out residual RF current to ground, but not so large as to short out the audio signal. When we say shunted in this context, we mean that the capacitor goes in parallel or in shunt with the headset. In the circuit of Figure 20-2, the diode recovers the audio from the radio signal. We call this process detection or demodulation, and we call the whole circuit a detector or demodulator. If we want the detector to function, we must use a diode that has low junction capacitance so that it can rectify at RF without acting like a capacitor. Some modern RF diodes resemble microscopic versions of the old cat's whiskers, enclosed in glass cases with axial leads. Frequency multiplication. When current passes through a diode, half of the cycle gets cut off as shown in figure 20-1b. This chopping off effect occurs regardless of the applied signal frequency from 60 Hz utility current through RF, as long as the diode capacitance remains small and long after the reverse voltage remains below the avalanche threshold. The output wave from the diode looks much different than the input wave. We call this condition nonlinearity. Whenever a circuit exhibits nonlinearity, harmonics appear in the output. The harmonics show up as signals as integer multiples of the input frequency, as we learned in Chapter 9. In situations where nonlinearity represents an undesirable state of affairs, engineers strive to make electronic circuits linear so the output waveform has exactly the same shape as the input waveform, even if the amplitude differ. But in some applications we want a circuit to act in a nonlinear fashion, for example when we intend to generate harmonics. We can deliberately introduce nonlinearity in a circuit to obtain frequency multiplication. Diodes work well for this purpose. Figure 20-3 illustrates a simple frequency multiplier circuit. We tune the output LC circuits to the desired nth harmonic frequency and NF subscript 0 rather than the input of fundamental frequency F. For a diode to work as frequency multiplier in RF systems, it must be of a type that would also work well as a detector at the same frequencies. This means that the component should act like a rectifier, but not like a capacitor. Signal mixing. When we combine two waves having different frequencies in a nonlinear circuit, we get new waves as frequencies equal to the sum and difference of frequencies of the input waves. Diodes can provide the nonlinearity that we need to make this happen. Consider two AC signals with frequencies F1 and F2. Let's assign F2 to the wave with the higher frequency and F1 to the wave with the lower frequency. If we combine these two signals in a nonlinear circuit, new waves result. One of the new waves has a frequency F2 plus F1, and the other has a frequency of F2 minus F1. We call these sum and difference frequencies beat frequencies. We call the signals themselves mixing products or heterodynes. The heterodynes appear in the output along with the original signals at frequencies F1 and F2. Figure 24 shows hypothetical input and output signals for a mixer circuit on a frequency domain display. The amplitude on the vertical scale or axis constitutes a function of the frequency on the horizontal scale or axis. Engineers see this sort of display when they look at the screen of a lab instrument known as a spectrum analyzer. In contrast, an ordinary oscilloscope displays amplitude on the vertical scale or axis as a function of time on the horizontal scale or axis, so it provides a time domain display. Switching. The ability of diodes to conduct currents when forward biased and block currents when reverse biased makes them useful for switching in some applications. Diodes can perform switching operations much faster than any mechanical device, up to millions or even billions of on-off operations per second. One type of diode, made for use as an RF switch, has a special semiconductor layer sandwiched in between the P-type and N-type material. The material in this layer is called an intrinsic or I-type semiconductor. The intrinsic or I layer reduces the capacitance of the diode, allowing the device to function effectively at higher frequencies than an ordinary diode can. A diode with an I-type semiconductor layer sandwiched in between the P and N-type layers is called a PIN diode. Figure 20 20-5. Direct current bias applies to one or more pin diodes, allowing us to effectively channel RF currents to desired points without using relays and cables. A PIN diode also makes a good RF detector, especially at very high frequencies. Voltage regulation. Most diodes have an avalanche breakdown voltage much higher than the reverse bias voltage ever gets. The value of the avalanche voltage depends on the internal construction of the diode and on the characteristics of the semiconductor material that compose it. Zener diodes are specially made to exhibit well-defined constant avalanche voltages. Suppose that a Zener diode has an avalanche voltage, also called the Zener voltage, of 50 volts, period. If we apply a reverse bias to the PN junction, the diode acts as an open circuit as long as the potential difference between the P and N-type materials remains less than 50 volts. But if the reverse bias reaches 50 volts, even for a moment the diode conducts. The phenomenon prevents the instantaneous reverse bias voltage from exceeding 50 volts. Figure 26 shows a graph of current through a hypothetical Zener diode as a function of the voltage. The Zener voltage shows up as an abrupt rise in the reverse current, and the reverse bias voltage increases. That is, we move toward the left along the horizontal axis. Figure 20-7 shows a simple Zener diode voltage regulator circuit. Note the polarity of the diode. We connect the cathode to the positive pole and the anode to the negative pole, opposite from the way we use a diode in a rectifier circuit. The series connected resistor limits the current that can flow through the Zener diode. Without the resistor, the diode would conduct excessive current and burn out. Amplitude limiting. In Chapter 19, we learned that a forward bias diode will not conduct until the voltage reaches or exceeds the forward breakover voltage. We can state a corollary to this principle. A diode will always conduct when the forward bias voltage reaches or exceeds the forward breakover voltage. In a diode, the potential difference between the P and N-type wafers remains fairly constant, roughly equal to the forward breakover voltage, as long as current flows in the forward direction. In the case of silicon diodes, the potential difference or voltage drop is approximately 0.6 volts. For germanium diodes, the voltage drop is roughly 0.3 volts, and for selenium diodes, it's around 1 volt. We can take advantage of the constant voltage drop property of semiconductor diodes when we want to build a circuit to limit the amplitude of a signal. Figure 20-8a shows how we can connect two identical diodes back to back in parallel with the signal path to limit or clip the positive and negative peak voltages of an input signal. In this configuration, the peak voltages are limited to the forward breakover voltage of the diodes. Figure 28b shows the input and output waveforms of a typical clipped AC signal. The downside of the diode voltage limiter circuit, such as the one shown in Figure 20-8a, is the fact that it introduces a distortion when clipping occurs. This distortion might not cause a problem for reception of digital signals, frequency modulated signals, or analog signals that rarely reach the limiting voltage, but for amplitude modulated AM signals with peaks that rise past the limiting voltage, clipping distortion can make voices difficult to understand, and it utterly ruins the sound quality of music. Frequency control. When we reverse bias a diode, we observe a region at the PN junction with dielectric insulating properties. As you know from the last chapter, this zone is called the depletion region because it has a shortage, a depleted supply of majority charge carriers. The width of the depletion region depends on several parameters, including the reverse bias voltage. As long as the reverse bias remains lower than the avalanche voltage, varying the bias affects the width of the depletion region. The fluctuating width, in turn, varies the junction capacitance. This capacitance, which is always on the order of a few picofarads, varies inversely with the square root of the reverse bias. Again, as long as the reverse bias remains less than the avalanche voltage, period. For example, if we quadruple the reverse bias voltage, the junction capacitance drops to half. If we decrease the reverse bias voltage by a factor of 9, then the junction capacitance increases by a factor of 3. Some diodes are manufactured especially for use as variable capacitors. Such a device is known as a veracitor diode, as you learned in the last chapter. Veracitors find their niche in a special type of circuit called a voltage-controlled oscillator. Figure 20-9 shows an example of the parallel-tuned LC circuit in a VCO using a coil, fixed capacitor, and a veracitor. The fixed capacitor, whose value should greatly exceed the capacitance of the veracitor, keeps the coil from short-circuiting the control voltage across the veracitor. The schematic symbol for a veracitor diode has two lines on the cathode side as opposed to one line on the symbol for a conventional diode. Oscillation and amplification. Under certain conditions, diodes can generate or amplify microwave RF signals, that is, signals at extremely high AC frequencies. Devices commonly employed for these purposes include the gun diode, the IMPAT diode, and the tunnel diode. Gun diodes. A gun diode can produce from 100 milliwatts to 1 watt of RF power output and is manufactured with gallium arsenide gas. A gun diode oscillates because of the gun effect, named after the engineer J. Gunn, who first observed it in the 1970s while working for International Business Machines Corporation. A gun diode doesn't work like a rectifier, detector, or mixer. Instead, the oscillation takes place as a result of a quirk called negative resistance, in which an increase in the instantaneous applied voltage causes a decrease in the instantaneous current flow under specific conditions. Gun diode oscillators are often tuned using veracitor diodes. A gun diode oscillator connected directly to a horn-shaped antenna gives us a device known as a gunplexer. Amateur radio experimenters use gunplexers for low-power wireless communication at frequencies of 10 GHz and above. IMPAT diodes. The acronym IMPAT comes from the word impact, avalanche, transit, time. The type of diode, like the gun diode, works because of the negative resistance phenomenon. An IMPAT diode constitutes a microwave oscillating device like a gun diode, except that it's manufactured from silicon rather than gallium arsenide. An IMPAT diode can operate as an amplifier for a microwave transmitter that employs a gun diode oscillator. As an oscillator, an IMPAT diode produces about the same amount of output power as at comparable frequencies as a gun diode does. Tunnel diodes. Another type of diode that will oscillate at microwave frequencies is the tunnel diode, also known as the Esaki diode. Made from the gas semiconductor material, the tunnel diode produces only enough power to function as a local oscillator in a microwave radio receiver or transceiver. Tunnel diodes work well as weak signal amplifiers in the microwave receivers because they generate very little unwanted noise. The noise characteristic is typical of gas devices. Energy emission. Some semiconductor diodes emit radiant energy when current passes through the p-n junction in a forward direction. This phenomenon occurs as electrons fall from higher to lower energy states within atoms. LEDs and IREDs. Visible light of almost any color can be produced by forward bias light emitting diodes, LEDs. Infrared emitting devices also exist. An infrared emitting diode, IRED, produces energy at wavelengths slightly longer than those of visible red light. The intensity of the radiant energy from LED or IRED depends to some extent on the forward current. As the current rises, the brightness increases, but only up to a certain point. If the current continues to rise, no further increase in brilliance takes place, and we say that the LEDs or IREDs is working in a state of saturation. Digital displays. Because LEDs can be made in various different shapes and sizes, they work well in digital displays. You've seen digital clock radios, hi-fi radios, calculators, and car radios that use LEDs. They make good indicators for on-off, AM, PM, low battery, and other conditions. In recent years, LED displays have been largely replaced by liquid crystal displays, LCDs. The LCD technology has advanced over LED technology, including lower power consumption and better visibility in direct sunlight. However, LCDs require backlighting in dim or dark environments. Communications. Both LEDs and IREDs work well in communications systems because we can modulate their intensity to carry information. When the current through the device is sufficient to produce output, but not so great as to cause saturation, the LED or IRED output follows along with rapid current changes. This phenomena allows engineers to build circuits for transmitting analog and digital signals over visible light and IR energy beams. Some modern telephone systems make use of modulated light transmitted through clear glass or plastic cables, a technology called fiber optics. Special LEDs and IREDs, known as laser diodes, produce coherent radiation. The rays from these diodes aren't the intense parallel beams that most people imagine when they think about lasers. A laser LED or IRED generates a cone-shaped beam of low intensity. However, we can use lenses to focus the emission into a parallel beam. The resulting rays have some of the same properties as the beams from large lasers, including the ability to travel long distances with minimal decrease in intensity. Photosensitive diodes. Most PN junctions exhibit conductivity that varies with exposure to radiant energy such as IR, visible light, and UV. Conventional diodes aren't normally affected by these rays because they're enclosed in opaque packages. Some photosensitive diodes have variable DC resistance that depends on the intensity of the visible IR or UV rays that strike the PN junctions. Other types of diodes produce their own DC in the presence of radiant energy. Silicon photodiodes. A silicon diode, housed in a transparent case and constructed so that visible light can strike the barrier between the P and N type materials, forms a silicon photodiode. If we apply reverse bias voltage to the device at a certain level below the avalanche threshold, no current flows when the junction remains in darkness, but current flows when sufficient radiant energy strikes. At constant reverse bias voltage, the current varies in direct proportion to the intensity of the radiant energy, within certain limits. When radiant energy of variable intensity strikes the PN junction of a reverse biased silicon photodiode, the output current follows the light intensity variations. This property makes silicon photodiodes useful for receiving modulated light signals of the kind used in fiber optic communications systems. Silicon photodiodes exhibit greater sensitivity to radiant energy at some wavelengths than others. The greatest sensitivity occurs in the near-infrared part of the spectrum, at wavelengths slightly longer than the wavelength of visible red light. The opto-isolator. An LED or IRED and a photodiode can be combined in a single package to construct a component called an optoisolator. This device, shown schematically in figure 2010, creates a modulated light signal and sends it over a small clear gap to a receptor. An LED or iRed converts the electrical input signal to visible light or IR. A photodiode changes the visible light or IR back into an electrical signal which appears at the output. An opaque enclosure prevents external light or IR from reaching the photodiode, ensuring that the photodiode receives only the radiation from the internal source. When we want to transfer or couple an AC signal from one circuit to another, the two stages interact if we make the transfer through a direct electrical connection. The input impedance of a given stage, such as an amplifier, can affect the behavior of the circuits that feed power to it, leading to problems. Optoisolators overcome this effect because the coupling occurs optically rather than electrically. If the input impedance of the second circuit changes, the first circuit sees no change in the output impedance, which comprises only the impedance of the LED or iRed. The circuit's impedances and the electrical effects thereof are literally isolated from each other. Photovoltaic cells. A silicon diode with no bias voltage applied can generate DC all by itself if enough IR, visible or UV energy strikes its PN junction. We call this phenomenon the photovoltaic effect. Solar cells work because of this effect. Photovoltaic cells are specially manufactured to have the greatest possible PN junction surface area, thereby maximizing the amount of radiant energy that strikes the junction. A single silicon photovoltaic cell can produce about 0.6 volts of DC electricity in daylight. The amount of current that it can deliver, and therefore the amount of power it can provide, depends on the surface area of the junction. We can connect photovoltaic cells in series parallel combinations to provide power for solid-state electronic devices such as portable radios. The DC from these arrays can charge batteries, allowing for use of electronic devices when radiant energy is not available, for example at night or on dark days. A large assembly of solar cells connected in series parallel is called a solar panel. The power produced by a solar panel depends on the power from each individual cell, the number of cells in the panel, the intensity of radiant energy that strikes the panel, and the angle at which light hits the surface of the panel. Some solar panels can produce several kilowatts of electrical power when the midday sun's unobstructed rays arrive perpendicular to the surfaces of the cells.